Hello, dear students. In today's session, we will discuss about design of journal bearing. So, the general design procedure is already discussed in previous session. Now, let us take an example of bearing design, that is journal bearing design used in a specific machine. Say, for example, here in the one of the previous video question paper uh, asked in July 2017, design a journal bearing used for a centrifugal pump running at 1200 rpm, carrying a load of 15,000 newtons, and journal diameter and length of the diameter, that is not given, length of the bearing is not given. Diameter of the journal is given as 100 mm, and length to diameter ratio is 1.5, and the temperature of the bearing surface is 50 degrees centigrade, and ambient temperature is 30 degrees centigrade. And here we have to uh, design the bearing, as well as we have to check whether artificial cooling is required or not here. So that the radius of the bearing or journal is 50 mm, that is d by 2, and rpm is converted into rps, that becomes 20 rps, n by 60. N is 1200 rpm divided by 60, that is 20 rps, revolutions per second. So according to this, here diameter and length both are not given. So in the beginning, what we have to do, use it with respect to the given machinery, that is centrifugal pump, we have to note down the recommended values by referring the data handbook. So select the recommended design parameters for the given type of bearing as well as machine. So you have to refer table number 15.7 of data handbook and page number 366. So there we have to note down around five parameters. Say first parameter is the maximum pressure. So maximum pressure is given in the range here, 0.7 to 1.4 Newton per mm square. And then the absolute viscosity Z is given as 0.025 Newton second per meter square. So this is also noted from the data handbook table. And Zn by P, which is also called as bearing modulus. So bearing modulus, that is what the minimum recommended value is 29.01. So this is what the minimum value. So the value what we have to adopt, that should be more than 29.01. And the ratio C by R is 0.0013, and L by D ratio is lies in between 1 and 2. So these are the recommended values or the design parameters, we can say, referred from the data handbook and taken from table number 15.7. So now the second step, that is the design. Design means here we have to fix the some of the values such as pressure, L and D, right? And absolute viscosity if it is expressed in terms of a range. Since pressure is expressed here in terms of lower and upper limit, that is 0.7 to 1.4 Newton per mm square. So select a suitable value, which is also called as allowable pressure value here, that is P is equal to 1 Newton per mm square. Or we can use the equation P equal to W by LD, or P equal to W divided by 2R into L. 2R is nothing but a small d itself. So here we know the values of small diameter. We know the value of small diameter, that is journal diameter 100 mm. So L by D ratio is also given here as 1.5. So the recommended value is lies in between 1 and 2. That means 1.5 lies in between 1 and 2. And length of the bearing, so if you multiply 1.5 to the diameter, that will be 150 mm. So the pressure value what we get here is 1 Newton per mm square itself. So what we have assumed, either by using this value you can get the values of L and D, or with the known value of L and D you can get the value of pressure 1 Newton per mm square here. And the ratio is lies in between 1 and 2, so that is suitable here. And C by R ratio is also given. So C is equal to, that is radial clearance, 0.0013 multiplied by the radius of the journal, that is equal to 0.065 mm. So the third step is to select the oil. So here the viscosity of the oil that is known, which is recommended, that is 0.025 Pascal second or Newton second per meter square. So here we know the bearing temperature of 50 degrees centigrade and ambient temperature of 30 degrees centigrade. So we want the value of operating temperature, that is T naught. So we have a standard equation, that is TB minus TA, bearing temperature minus ambient temperature, is equal to T naught minus TA divided by 2. So by using this equation, you can get the value of T naught, which is obtained here as 70 degree centigrade. So with respect to 70 degrees centigrade, and we have to assume a specific gravity of zero point 0.9. So this is assumed here based upon the values given in table number 15.1. So in 15.1, if you take all the average of all the values, that will be around 0.88, 0.89 like that. So here we have assumed a standard value of zero point 0.9, which is a specific gravity of assumed oil. And anyway, the value of absolute viscosity that is known 0.025 pascal second, that is noted in the very first step. So here we have to note down the value of kinematic viscosity, since in our data handbook referring figure number 15.3, so there we have to refer a particular chart, temperature, operating temperature versus kinematic viscosity. So absolute viscosity is known here. Convert that absolute viscosity into kinematic viscosity. So kinematic viscosity is nothing but the absolute viscosity divided by the mass density. So kinematic viscosity is the ratio of absolute viscosity to the mass density. So mass density is calculated here by with the help of specific gravity. Specific gravity of oil multiplied by the standard mass density of the say mass density of the standard fluid, that is water. That gives the mass density of the respective liquid. So now, zero point 0.9 is the specific gravity of that oil multiplied by standard density, that is 1000. That is density of standard fluid, that is water. So rho into 1000, that is mass density. So that is nothing but in the data handbook or in a design procedure, we have written that equation as Z divided by rho into 10 raised to minus 3. That is nothing but Z divided by rho into 10 raised to plus 3. So by using this equation, we will be getting the value of Zk, that is kinematic viscosity, 2.78 into 10 raised to minus 5 meter square per second. So this is what in SI unit. But we want the unit of Zk to refer that figure in the data handbook in centistroke. So convert the above value in terms of centistroke by dividing that value by 10 raised to minus 6. So if I divide that value by 10 raised to minus 6, so the value what is obtained here is 27.8 centistroke. CST means centistroke. Now refer figure number 15.3 given in page number 352 with respect to the operating temperature along the abscissa or the top abscissa 70 degrees centigrade, and Zk kinematic viscosity 27.8 centistroke along the ordinate, which is given on the right side of that figure. So if these 2 points are taken, so that these 2 points, if they are extended, they are going to intersect on a curve which is F curve here. So the line or the curve which is obtained with respect to these two values is F curve. So according to this F line, so F line indicates SAE 30, which is referred or which is noted from table number 15.1, page number 363. So this is what the procedure to know the select the name of the oil. Anyway, the absolute viscosity is known. Absolute viscosity is converted into kinematic viscosity by multiplying absolute viscosity by the specific gravity multiplied by 1000, which is in terms of meter square per second, and that is divided by 10 raised to minus 6, so that is in centistroke. So with respect to this value and operating temperature, name of the oil or the curve is selected first, and then table number 15.1 gives name of the oil, which is SAE 30. So in some of the cases, you may get that value, that name as SAE 40 also, no doubt. So no problem that you can proceed. But here this particular step is important. Check for the oil. So if you use this equation, C calculated, that is bearing modulus calculated value, Zn by P, Z is 0.025 multiplied by 1200 RPM divided by pressure 1. So the value what we get here is 30, but the recommended value is 29.01. Hence, this calculated value is greater than the recommended value, so that we can come to a conclusion that the oil or the film which is formed here is a thick film. Hence, the oil which is selected is suitable. Oil Se30 with a absolute viscosity of 0.025 Newton second per meter square is suitable. And then we have to proceed with the heat generated calculation. So heat generated is given by F into W into V, which is given in equation number 15.11a, page number 360. And F is coefficient of friction. So here this is not a lightly loaded journal bearing. This is a heavily loaded journal bearing. Equation number 15.4b, page number 353, and assume the full bearing. So the equation which is given here is F is equal to Ka into Zn by P uh, into R by C into 10 raised to minus n 10 plus delta F. Ka is 0.195 into 10 raised to 6 for beta equal to 360 degrees, that is full bearing, and delta F is 0.002 and L by D is 1.5. For this value is suitable. So after substituting, what we get here is the value of F as 0.0095. So substitute that value of F in the equation of heat generated, and here V value is 6.283 meter per second, which is V is equal to pi d n by 1000, that is small n by 1000. So Hg what we get here is 895.36 joule per second. Similarly, heat dissipated calculation. So you can use the equation 15.11b, page number 360. So heat dissipated is given by Kh into A dash into Tb minus Ta. Kh is 11.4 joule per second meter square per degree centigrade, and area is 20 times dl into 10 raised to minus 6. So if you substitute all the values in the equation, so heat dissipated is given by or obtained here as 68.4 joules per second. So this value is less as compared to the value of heat generated. Since heat generated is greater than heat dissipated, so the amount of artificial cooling that is required here, right? That is what heat generated minus HD, that gives a value, positive value. Hence, that is the amount of heat that is to be removed. Hence, artificial cooling is required here. Next, the particular value, the parameter that we have to calculate here is minimum film thickness, MFT. So before proceeding with the minimum film thickness, we have to calculate minimum film thickness variable, or we have to note down minimum film thickness variable, which is H naught by C. So this is given in equation number 15.7a, page number 356. So to refer to get this value, we have to calculate Sommerfeld number first. So Sommerfeld number without side leakage, that is given in equation number 15.6a, page number 354. So S is given by R by C whole square uh, into Zn by P into 10 raised to minus 6. So this value is 17.75. So now we refer the figure number 15.9, page number 356 of the data handbook, with respect to beta value 360 degrees. 360 degrees. So the value of H naught by C that is obtained here is 0.92. 0.92. So this 0.92 is multiplied by this C, so that minimum film thickness is equal to H naught, that is equal to 0.92 into 0.065. So that H naught is 0.0598 millimeters. So this is what minimum film thickness. And similarly, you can calculate the location. That is what epsilon location is given by 1 minus H naught by C is equal to cos phi. So phi is equal to cos inverse of 1 minus 0.92. So that value is to be expressed in terms of degrees. Next, we have to go for the calculation of flow rate. So flow rate is again calculated by assuming there is no side leakage. Without side leakage, that is Q is equal to FLV into RC into NL. So equation number 15.8b, page number 358. So here also with respect to Sommerfeld number, which is calculated in the previous step, that is 17.75, and beta equal to 360 degrees. So if you refer figure number 15.13, page number 358 of data handbook, so the value of FLV, that is flow variable, is 3. So this flow variable value that is noted from the graph, that is figure 15.3 with respect to S and beta value. So here the value of FLV3, if it is substituted, R is radius 50 mm, C is radial clearance 0.065, N is RPM 1200 RPM, L is length of the bearing 150 mm. So that the value of Q that is obtained here is uh, 17 lakh 55,000 mm cube per minute. So convert this mm cube to meter cube. So if you divide this one by 10 raised to 9, then the unit will be meter cube. And again divide this one by 60, that will be in seconds. So that the answer what we get for Q is you have to multiply. So convert mm cube per minute to meter cube per second. You have to multiply 10 raised to minus 9 and divide it by 60. So the answer what we get here is 2.92 into 10 raised to minus 5 meter cube per second. That is what the flow rate Q. And power loss is given by Fw into V divided by 1000, which is nothing but heat generated per second. That is in kilowatt. That itself is power loss. So 895 divided by 1000. So that value is 0.895 kilowatts. So this is what the procedure or according to the general procedure itself, that we have to calculate all the things related to the application oriented problems. So application oriented problems means initially we have to note down the recommended values. So recommended values gives the values of pressure, absolute viscosity, and then bearing modulus, that is the minimum value, and then C by R, that is the radial clearance ratio, after that L by D ratio. So based upon these five parameters, the second step is to fix the important values such as dimensions, usually L and D. So if you don't know the diameter and the length, pressure is to be fixed. Say allowable pressure is fixed in between those two limiting values, zero point 0.7 to 1.4. So one is fixed here. So by using that pressure value with the by using L by D ratio, we can get the value of L and D, or with the known values of L and D, we can get the value of pressure, and we have to check that pressure whether is it lies in between this range or not. So that is the second step. Third step, to select the oil. No doubt we know the absolute viscosity. So operating temperature is also known, and where we have to assume specific gravity as zero point 0.9 standard, and also we have to calculate the zk value. Zk value is what? Z by rho into 10 raised to 3. Rho is specific gravity and 10 raised to 3 is the mass density of the standard fluid, which is water. So the answer what we get is in meter square per second, and that is to be converted into centistokes by dividing the obtained value by 10 raised to minus 6. The answer what we get is 27.8 centistoke, and we have to refer figure 15.3, which is having along ordinate the centistoke value of kinematic viscosity and operating temperature on the top abscissa. So if we use these two values of operating temperature and Zk in centistoke, what we select here is name of the curve, and then we have to fix the name of the oil, or we have to name the oil by referring table number 15.1. Like that we have to check the oil. So here we have to calculate the minimum of bearing modulus. So bearing modulus, that is more than the recommended value, which is obtained here as 30. Hence the oil is suitable. Then as usual, heat generated, that is Fw into V. F is calculated by using Mackey's equation. So full bearing is to be assumed. So and that value is to be substituted, and Hg is obtained here in joules per second. And then heat dissipated, and compare Hg and Hd. If Hg is greater, Hd is less, then we can conclude that artificial cooling is required. And what is the amount of heat that is to be removed? That is Hg minus Hd. Then minimum film thickness, and after that flow rate. So these two are to be referred from the figures, say 15.9 and 15.13 for flow rate. And after that we have to calculate the power loss. So this is what the method to calculate the things related to the application type problems. That is what design of complete journal bearing. So I hope you have followed the procedure. Thank you.